we have to maximize AV, that is number of molecules with respect to temperature, as dy dt AV equals to n into m by 2 pi kt to the power 3 by 2 into dy dt e to the power minus mv square by 2 kt into 4 pi v square dv plus n into 4 pi v square dv e to the power minus mv square by 2 kt dy dt m by 2 pi kt to the power 3 by 2 equals to n into m by 2 pi kt to the power 3 by 2 to e to the power minus mv square by 2 kt into mv square by 2 kt square into 4 pi v square dv plus minus 3 by 2 into n into 4 pi v square dv into e to the power minus mv square by 2 kt into m by 2 pi kt to the power 3 by 2 into 1 by t to the power 5 by 3 for maximum value of fv by dt equals to 0 equals to n into m by 2 pi kt to the power 3 by 2 e to the power minus mv square by 2 kt into mv square by 2 kt square into 4 pi v square dv minus 3 by 2 into n into 4 pi into v square into e to the power minus mv square by 2 kt into m by 2 pi kt to the power 3 by 2 into 1 by 2 equals to 0. This implies mv square by 2 kt square minus 3 by 2 into 1 by t equals to 0. This implies mv square by kt equals to 3. Hence t equals to 1 by 3 mv square by k. Answer. Find the fraction of molecules whose velocity projection on the axis fall within the interval from Vx to Vx plus dVx, while the moduli of perpendicular velocity components fall within the interval from V perpendicular to V perpendicular plus dV perpendicular. The mass of each molecule is m and the temperature is T. From the Maxwellian distribution of gas, dnv equal to n into m by 2 pi k to the power 3 by 2 into 4 pi v square dv into e to the power minus mv square by 2 kt, which gives the velocity distribution irrespective of direction. Now let if 4 pi v square dv is replaced by dvx, dvy, dvz, where then dnv equals to n into m by 2 pi kt to the power 3 by 2 e to the power minus mv square 2 kt into dvx, dvy, dvz, which gives the number of molecules of an ideal gas moving with velocity having components in the range Vx to Vx plus dVx, Vy and Vy plus dVy. Now if 2v square dv equals to dvx, dvy, v1 dv1, now dnv equals to n by m by 2 pi kt to the power 3 by 2 into 2 pi into e to the power minus mv square by 2 kt into v1 dv into dvx. Answer. Using the Maxwellian distribution function, calculate the mean velocity projection average of mean Vx if the mass of each molecule is equal to m and the gas temperature is T. Use the Maxwellian distribution function dvn equals to n into m by 2 pi kt to the power 3 by 2 into 4 pi v square e to the power minus mv square by 2 kt dv, and also use the definition of average velocity. Mean of average x equals to 0 to infinity v dvn by 0 to infinity dvn. We get the result average of Vx is equal to 0 and average of mean Vx equals to root 2 kt by pi m. Also used for average Vx. dnv2 equals to n into m by 2 pi kt to the power 1 by 2 into e to the power minus mvxr by 2 kt dvx. From the Maxwellian distribution function, find average of v square x, the mean value of the squared vx, projection of the molecular velocity in a gas at temperature T. The mass of each molecule is equal to m. We know